In the spring of 1905, a storm broke out in the mind of Albert Einstein. At least that is how Einstein himself described it later in life. And the result of that storm of thinking is the special theory of relativity, a theory that completely transforms our understanding of space and time and matter and energy. I mean, Einstein found, completely counter to experience, that clocks in motion tick off time at a slower rate. He found that objects in motion are contracted along their direction of motion. He found that clocks that one set of individuals say are in sync relative to each other, he found that if someone's moving relative to those clocks, they would say they're not synchronized. And of course, he also found the most famous equation in all of physics, E equals mc squared, establishing this deep, hidden connection between mass and energy. Now, you should say to yourself, if there is such an unexpected nature to reality that we have missed through our everyday experience, why have we missed it? I mean, why aren't we aware of special relativity right in our bones? And the answer to that is, when we look out at the universe, we recognize that there are a huge range of scales that constitute reality. And we humans only have access to a very small part of that totality. So to give you a feel for that, let's look at one axis, a length axis. And if you look at the scales that are out there in length, atoms, 10 to the minus 10 meter, viruses, 10 to the minus 8 meters, red blood cells, 10 to the minus 6, single-celled organisms, there we humans are, 2 meters, the Earth, 10 to the 5 meters, solar system, 10 to the 13, galaxy, and on to the observable universe itself. A huge range of scales when it comes to length, and we humans really only have direct access through experience to a small part of that. And that's only the axis of length. Imagine we look at the axis of mass. There too, we will find a huge range of scales, right? So if we go back and look at atoms, they weigh in 10 to the minus 26 kilograms, go down to red blood cells, 10 to the minus 15. Humans, well, depends who you're talking to, but about, 100 kilograms or so. Solar system on to the entire universe, the observable part, 10 to the 52 kilograms. A huge range of scales in mass. We humans only have direct access to a small piece of it. One more axis to look at is the axis of speed. So we humans, we walk around the world at certain ordinary everyday speeds. Sometimes we go into airplanes, but there's a huge range of speeds out there. The growth of human hair, that's pretty small. Human speed, typically, space shuttle, 10 to the 3 meters per second. Speed of light, that's a number that's going to come up a lot in our discussion, 10 to the 8 or so meters per second. The point is, in this spectrum of all possibilities, in length, in mass, and also in speed, we humans occupy a tiny, tiny part. So our experience, the experience that has given us our intuition, is built up from a very limited sense of what is actually out there. So our intuition, which really has come in some sense from evolution, right? So we evolved out there in the jungle, and our intuition got built up in order that we can survive. The survival value of understanding your environment is what matters. We humans only have access to a small piece of the totality of what's out there, and therefore it would be surprising if what we have experienced really does tell us about the physics at all possible scales, in length, in speed, and in mass. And it turns out that indeed it is the case that when you look at extremes of mass or length or speed, the world operates, the universe operates in ways that we are not accustomed to. If you are looking at extreme, say, a very small size, the new physics that comes into play is called quantum mechanics. If you are looking at extremes of huge mass, the new physics that comes into play is the general theory of relativity. If you are looking at extremes of speed, how the universe behaves at very, very high speeds, then it is the special theory of relativity that comes into play. That is what we are going to be discussing. So in a nutshell, all of the discussion we are going to be having here is focused upon how the universe behaves at very high speeds. That is the special theory of relativity. Since speed is the fundamental core of what drives the special theory of relativity, let's start at the beginning and ask the most basic question of all, which is, what is speed? Well, we all know the answer to that, but let's get all on the same page. So if that car, say, has a speed of 100 kilometers per hour, we all know what that means. If we look at how far it's gone divided by how long it takes it to get there, so let's say this is 1 hour journey. If it's going 100 kilometers an hour, we know that it will have traveled 100 kilometers in that hour. That's what speed is. So in essence, speed is nothing but distance that an object travels divided by duration. Now, expressed in that language, speed might seem like, I don't know, a kind of boring concept, a pedestrian concept. Why concern yourself with speed? The answer to that is clear if we recognize that distance is a measure that has to do with space. Duration is a measure that has to do with time. So if we find, as we are going to find going forward, that speed has unusual features when the speeds involved get very big, near the speed of light, what we really will therefore be learning is that space and time have weird, strange features. That is what we are after. Okay, good. That's where we're headed. Let's start by first thinking about the non-strange features of speed, the features that we all hold in our intuition. So what are the basic features of speed? Well, first off, speed is a concept that even before Einstein was known is a concept that is relative. What do I mean by that? Well, imagine we look at this car, say it's going 100 kilometers per hour. What we need to say is 100 kilometers per hour relative to the road. Why? If that road is itself moving, let's say it's on a boat, the boat is moving, then the car's speed relative to the water is not 100 kilometers per hour. And if we zoom out and look at that car on the surface of the Earth, and we realize that the Earth itself is spinning around, the Earth itself is going in orbit around the sun, with respect to the frame of reference, our perspective right now, that car is executing a pretty complicated motion, not just 100 kilometers per hour. So it's always vital when you're talking about speed to recognize that you can only ever frame the idea of speed for ordinary objects that we encounter as the object has this and that speed relative to this or that object. You need to specify the reference in order that the speed that you are specifying has any meaning at all. Okay, so that's a very basic feature of speed, that it is relative. Another basic feature of speed is that it is additive and subtractive. So what do I mean by that? Well, let's imagine that we have two characters who are playing a game of catch with, say, a football. George and Gracie, two characters that we are going to encounter often in our discussions. And imagine that they're throwing that football back and forth at, say, 5 meters per second. Now, that's all well and good, completely understood. But let's imagine that they go out to play a game of catch on another day, and Gracie is surprised to see that George has a hand grenade. Now, she doesn't like hand grenades, and so she runs away when he throws it because she knows that by running away from the hand grenade, she can change the speed at which it approaches her. She can subtract her own speed from the speed of the oncoming grenade, and in that way have it approach her not, say, at the initial speed at which it was tossed, which, for instance, might be just like the football, 5 meters per second. Instead, if she runs away at 3 meters per second, she knows that now the grenade will approach her more slowly at 2 meters per second. And that is a good thing when it comes to hand grenades. Similarly, it's the case that if an observer like Gracie is to not run away, but say run toward an object that is being thrown at her, the speed with which she approaches the object will be added to the rate at which it approaches her. So if it was thrown at 5 and she's running toward it at 3, well, we all know that that means it will approach her at 8 meters per second. Speed is additive and subtractive. You can change the speed with which an object is coming toward you by either running toward it or away from it. Now let me quickly mention, just as a small footnote, these basic calculations that we've done here, we surprisingly are going to find that they are only approximate when you take into account some of the strange features of relativity, but that's something that we will encounter later, especially if you're doing the math version of this course. But in terms of the basic idea that comes from our intuition, you certainly would anticipate that if you run toward an object, its speed will approach you more quickly. If you run away from an object, it'll approach you more slowly. Third basic feature of speed that, again, we are all familiar with is this. When you are executing a very special kind of motion, what we call constant velocity motion, motion that has a fixed speed, fixed magnitude, and a fixed direction, then you can't feel that motion, right? You can't feel that motion for a very good reason. If you are executing constant velocity motion, you are completely justified in claiming to be at rest and the rest of the world moving by you. In that sense, constant velocity motion is very special because it is motion that is completely subjective. There is no absolute notion of being in motion when the velocity is constant. So let me give you a quick example of that. So let's imagine that we have one and the same physical situation described from two different perspectives. So what I'm going to imagine is having George and Gracie floating in space, okay? Floating in space. Now here's George's view of the events. He looks out and he sees a character, Gracie, coming toward him, and she waves as she passes, as does he. His perspective is that he is stationary and she is rushing by him. Good. Now, I'm going to show you exactly the same situation, but from Gracie's perspective. So what does Gracie say? From her perspective, she says that she is stationary out there in space. She looks out into the distance, and she sees George rushing by. He waves, she does too, and he goes on his merry way. Is one perspective right and the other wrong? Absolutely not. You are completely justified if you're not accelerating, if you aren't changing your speed or changing the direction of motion, to say that you are stationary. Now, the reason why I'm emphasizing constant velocity motion is something that you have all experienced, right? If you are in a car and you take a sharp turn, you feel your body being pushed this direction, you know that you are moving. If you are in an airplane and it's taking off, as it accelerates, as it speeds up, you feel yourself pushed back into the seat. You know that you are in motion. But if you're not accelerating, you don't feel the motion, and in fact, there is no way for you to detect the motion at all. So for instance, if you imagine that George and Gracie were in two floating laboratories out there in space, and they do experiments to work out the laws of physics, they will work out exactly the same laws because there will be absolutely no remnant, no experimental implication of their relative motion if that motion is at constant speed in a fixed direction. No way to determine your state of motion because you are justified in saying that you are at rest. Now that idea that you can claim to be at rest, that there's no implication of constant velocity motion, does not start with special relativity. It does not start with Albert Einstein. This is an idea actually that goes way, way back. It goes all the way back to Galileo. And Galileo wrote a wonderfully poetic description of this idea. Let me show you a little visual representation of what he said, and I'll just read his words to you while this plays. So he said, "Shut yourself up on a large ship, and there procure gnats, flies, and other small winged creatures." He said, "Let a bottle be hung up, which drop by drop lets forth its water into another narrow-necked bottle placed underneath. Then, with the ship lying still, observe how the winged animals fly with like velocity toward all parts of the room, how the distilling drops all fall into the bottle placed underneath. Then," he says, "having observed all these particulars, make the ship move with whatever velocity you please." So here it is, the ship is going into motion, and he says that so long as the motion is uniform, by which he means constant velocity, you shall not be able to discern the least alteration in all the forenamed effects, nor can you gather by any of them whether the ship is moving or standing still. That is the very same idea, that constant velocity motion cannot be detected. It has no impact on your observations. Old idea, back with Galileo. So where then does Einstein come into this story? Einstein's new contribution is to say that among the forenamed effects that Galileo was talking about, he was just talking about the gnats and flies and the water dropping into the bottle placed underneath, that those things would not change if you go into motion so long as it's uniform. Einstein added something to the list. Einstein added to the list of things that would not change, he added the speed of light. This is the surprising new insight of Einstein. Let's see what it means. The speed of light is constant, right? That is one of the most famous sentences in all of science. The speed of light is constant. Now, what does it mean, and why should you care? Well, to get there, let's think about how it is that Einstein came to this idea that the speed of light is constant. It's an interesting history where over the course of many centuries, many people struggle to understand light. And perhaps a good place to pick it up is in the 1600s to the 1800s, when a whole group of physicists spent a lot of time, put a lot of effort into trying to measure the speed of light, and they did a pretty good job. Romer, Huygens, Bradley, Fizeau, Foucault, these guys, some of whom had very long hair, made increasingly precise measurements of the speed of light. With modern updatings, we now know that the speed of light is 671 million miles per hour. If you like those units, it's 300 million meters per second, or a little bit more precisely, it's 299,792,458 meters per second. But we will round that off to 300 million meters per second for the most part. So that was good. People understood the speed of light. But even so, physicists lacked an understanding of what light actually was. And that's when two physicists, Michael Faraday and James Clerk Maxwell, who through experiments, mostly Faraday, through theorizing, mostly Maxwell, they realized something quite amazing. Because they studied electromagnetic waves. They studied ripples in an electromagnetic field and came to a stunning conclusion. So Maxwell did this mathematically based upon the experimental results of Faraday, and roughly speaking, what Maxwell ultimately concluded from the equations, from the math, was that an electromagnetic disturbance always travels at a particular speed, regardless of the wavelength, which is the distance between one crest and another. And remarkably, the speed that he found for electromagnetic waves, again, independent of whether they have a very long wavelength or if, for instance, they have a much shorter wavelength, like this fella coming in here, he found in the equations that the speed of those electromagnetic disturbances would always be equal to a particular number, and that number turned out to be 671 million miles per hour, or 300 million meters per second. So this was a stunning insight. And again, if you haven't studied electromagnetism, it doesn't matter. All that matters here is that Maxwell had these equations, and from the equations out came, from a calculation, a speed that was equal to the speed of light. What was Maxwell to conclude? Well, naturally, he said, if the speed of the electromagnetic disturbances is equal to the speed of light, then light itself must be an electromagnetic disturbance. It must be an electromagnetic wave. That was a great step forward. Now we had an understanding of what light actually is. But even with the progress that that represented, it still raised a profound mystery. And that mystery is this. As we described before, whenever you talk about speed, you need to say an object has this speed relative to that object. You need to state things in that manner for speed to even have any meaning, right? But when it comes to the equations that Maxwell was studying, they didn't specify what speed, 671 million miles per hour, was relative to, right? So if you have sound waves, the speed of sound is relative to the still air. If you've got water waves, the speed of the water wave is relative to the still water. What was the thing relative to the speed of light was being calculated? Nothing seemed apparent, so physicists dealt with this mystery by making up an answer. They said maybe there is something called the ether filling space, and when you talk about the speed of light, you're talking about the speed of this electromagnetic wave relative to the ether. Experiments were done to try to find the ether, and to make a long story short, no evidence for the ether whatsoever. So the puzzle remained. This is where the genius of Einstein comes into the story. Because Einstein had this uncanny ability to look at something that everybody else had been staring at and see it in a new way. And Einstein said, look, if the equations are saying that the speed of light is 671 million miles per hour, but the equations are not specifying what that speed is relative to, maybe that's because you don't need to specify anything. Einstein said the speed of light is 671 million miles per hour relative to anything, so long as it is traveling through empty space. Now, this is a strange idea. It is a maverick idea. You might say it's a crazy idea because we are unused to any speed that isn't relative. We are unused to any speed that, for instance, can't be changed by running toward it or away from it. But that is what Einstein was saying. So let me give you just a little visual example of what this constant speed of light, this fact that Einstein was saying that you don't need to specify the reference for the speed of light. It is just a number, a law of physics. Here is what that would imply. So imagine we have George and Gracie out there again. Gracie has a meter that can measure the speed of light. When she's standing still, George fires his laser beam, and she gets 300 million meters per second. But now let's change things just a little bit and imagine that Gracie runs away. You would think the speed should be less because she's running away, but no. Einstein would say it's still 300 million meters per second. It is a constant. It is a law of nature that the speed of light is that number relative to anything. Similarly, if Gracie were to run toward George, you'd think the speed would go up because she's running toward the oncoming laser beam. No, 300 million meters per second again. And the same thing would hold true if it's not Gracie that's running, but George. So the source, if the source is running, you'd think the speed should be a little bit bigger, 300 million meters per second, not 1 iota bigger. And similarly, if George were to be running away, you would think that the speed she should measure should be smaller than 300 million meters per second, but it remains, according to Einstein, the same fixed number, a constant, 300 million meters per second. Now, if this is true, right? This is Einstein's idea. If it's true, it's telling us, as we mentioned before, that speed has some very unusual properties when you're talking about speeds that are very fast, near the speed of light. 300 million meters per second or 671 million miles per hour is very fast, fast enough to go around the Earth 7 times in a single second. And what Einstein is saying, at those speeds, you begin to reveal a feature of nature that you would not anticipate based upon footballs or hand grenades or any of the ordinary objects of everyday experience. So if it's true, if speed has these weird features when you're talking about speeds near the speed of light, then that would mean that space and time, because speed, distance over duration, space over time, it would mean that space and time have weird features. That's why this is such a critical idea. But of course, the essential question is it right? Is the speed of light actually constant? We care about the speed of light being constant because speed, again, is a measure of space per time. So if speed does something weird, then that must mean, as we've emphasized already, that space and time must be doing something weird too. And in this section, we're going to describe one of the most startling implications of the constant nature of light speed, which is that there is no universal agreement on what things happen at the same time. That's where we're going. Now, to get there, let's start with the basic intuitive understanding of time, right? So over the course of many centuries, we humans have gotten pretty good at learning how to measure time. We have developed all sorts of clocks that through the ages have gotten better and better and better at measuring the time interval between one event and another with absolutely astounding accuracy. Now, having said that, we have still struggled for ages to really understand what time itself actually is. We don't yet have an answer to that question, but we do have certain basic understanding of the properties of time. For instance, we all agree that clocks that are properly functioning and properly set, all of those clocks will tick off time at the same rate, so they will all be in sync with one another. They will all agree with one another. We also generally agree that individuals that are measuring the duration of an event with properly functioning clocks will get the same answer. We all agree on how long it takes for something to happen, and we all agree, generally speaking, on what things happen at the same moment, right? Those are the basic features of time as we experience time in everyday life. Here is the thing. The constant nature of light speed says that all of that is wrong. It tells us that properly functioning, properly set clocks do not generally agree with one another. It tells us that we generally do not all agree on what happens at the same moment in time, and we generally will not all agree on how long it takes for something to happen. Now, those are some pretty striking claims. I'm not going to describe all of them right now, but we're going to take on one of them. I want to describe how it is that the constant nature of light speed ensures that different perspectives of individuals that are moving relative to each other will not agree on what events happen at the same time. And to do that, I'm going to frame it in the context of a little story. The story goes like this. Imagine that there are two warring nations, forward land and backward land, and they've just come to an agreement. They're ready to sign a treaty, except each president stipulates that he does not want to sign the treaty before the other. So the Secretary General of the United Nations needs to come up with a plan that convinces them that in the procedure that they are going to use, each president will sign at the same moment. Here's the procedure that the Secretary General comes up with. He says, look, we're going to have you both sit at opposite ends of a table. We're going to put a light bulb in the middle. We'll turn on the light bulb. When the light reaches your eye, you sign the treaty. You're equidistant from the bulb, and therefore it should take the same amount of time for the light to reach you. You should sign simultaneously. So here is the setup. The light goes off. The flash goes toward each of the two presidents, hits them, and they sign the treaty, and they are all very, very happy. Good. Now, they are all very happy that this agreement has been reached, and a few months later, they come to another agreement that they want to sign at the same moment, except this time both presidents want to do it a little differently. Even though they have many, many differences, each of the presidents of forward land and backward land, they both have a deep love of trains. So they want to do the treaty signing ceremony on a train that is going right across the border between forward land and backward land. So they set up the same scenario, and here they are on the train. Train is going along. There is a table again in one of the cars. The presidents are equidistant on the train from the bulb. The bulb will be turned on just as in the previous case, and when each president sees the light, he will sign the treaty. Okay, so here we go. The bulb goes off, the light flashes, goes toward each of the presidents, and they sign the treaty, and everybody on the train is again very, very happy with the result. But here's the thing. Just after they sign the treaty, word comes that the people on the platform are fighting. They're fighting because those folks from forward land claim that they have been duped. They claim that their president from forward land signed the treaty first. How could they come to that conclusion? Well, here's how it goes. So the people from forward land, they are on the platform watching this happen. And from their perspective, look what happens. When the flash goes off, the president of backward land is moving away from the flash from their perspective, so it takes longer to reach him than the president of forward land who's moving toward the flash. So let me show you that again. Watch what happens when the flash goes off. The president of forward land moves toward the flash. President of backward land moves away from the flash. The light has to travel further to reach the president of backward land than the president of forward land. It has the same speed. The speed of light is constant. So if it has to travel further, it's going to take longer to get there from the perspective of those people watching on the platform. And therefore, they claim that the two presidents did not sign at the same moment. They claim that the president of forward land signed the treaty first. Let me show you one more variation on that so you can really see the detail of what's going on. This time I'm going to draw a line where the flash takes place. There's where the flash took place. Look how far the light has to travel to reach the present of forward land versus backward land. It only has to travel this distance to reach forward land. It has to travel this distance to reach the present of backward land. Light travels at the same speed. If it has to travel further, it's going to take longer to get there. So we now have an interesting situation. Those people on the train are absolutely convinced that the two presidents signed at the same moment. Those people on the platform are just as convinced that they did not sign at the same moment. So the big question is, who is right and who is wrong? And the answer is, they are both right. The reasoning of each group of individuals is absolutely impeccable. For those on the train, the presidents are equidistant from the bulb. Bulb lights up. The light travels the same distance to each, so they sign at the same moment. Perfect reasoning. Those on the platform, they say the flash goes off and it doesn't have to travel as far to president of forward land as it does to the president of backward land. Speed of light is constant, and therefore they do not get the flash at the same moment. That reasoning is absolutely impeccable. So what this is telling us is that the constant nature of the speed of light means that events which take place at the same time from the perspective of one group of individuals will not take place at the same time from the perspective of another group of individuals moving with respect to them. Now, this relies, of course, on the constant speed of light, because what Newton would have said is he would say the projectile, say the light, will get an additional kick from the train moving in this direction, and that additional speed will allow it to cover this distance in the same amount of time. The light going this way would have its speed diminished, and therefore it's traveling a shorter distance. And when you take those two effects into account, Newton would say both of the presidents get hit at the same time, regardless of your vantage point. But because of the constancy of the speed of light, we come to a very different conclusion. This is what's known as the relativity of simultaneity, and is one of the most startling implications of the constant nature of light speed. The relativity of simultaneity strongly hints, in fact, almost necessarily requires, that motion, speed, must be affecting time itself. The rate at which time passes must be affected by motion. That's the only way that we really can conclude, as we have already, that simultaneity depends upon your perspective. I mean, in the treaty signing ceremony, if clocks on board the train agreed with clocks on the platform, then everyone would agree on what happens at a given moment. Everyone would agree on whether the president signed at the same moment. But they don't agree. And so clocks that are moving relative to each other must tick off time differently. Now, for us to make that idea precise, to us to really understand how it is that motion affects the passage of time, we need a way of measuring the passage of time. We need, of course, a clock, right? Now, you can use, for all that we are talking about here in relativity, you should feel free to use any clock that you like, right? Your favorite Rolex, your favorite grandfather clock, any clock that you'd like to use. I, however, am going to make use of a special kind of clock that's quite unfamiliar, but as you will see, it's a very powerful kind of clock for assessing the effect of motion on time. So I should spend just a moment addressing the issue of what is a clock, right? So what is a clock? A clock is any physical system that undergoes cyclical repetitive motion, and it does that cyclical motion. It undergoes those cycles in a uniform way, right? So if you're talking about using the Earth as a clock. The Earth spins around its axis in a uniform way, and we use that to say every time it goes around once, that's a day. We can talk about the Earth in revolution around the sun, right? It does that in a fairly uniform cyclical way, and we call each revolution a year. And on a more standard wristwatch, if you have, well, I should say one of the old-fashioned ones that has a second hand that's sweeping around, it does that sweeping motion cyclically, sweep after sweep after sweep, and we call each of those sweeps a minute, right? So that is what a clock is, conceptually. The new kind of clock that I'm going to introduce has that same kind of feature. Cyclical motion, a cyclical process happens over and over again, but the process itself is a little unfamiliar because the kind of clock that I'm talking about is called a light clock. What is a light clock? A light clock is a contraption in which we have two mirrors that are facing one another, and a ball of light will bounce in between them. And every time the ball goes up and down, you can think of that as tick-tock, right? Tick-tock. The ball is just going up and down. So let me show you a quick visual of this kind of clock, this light clock. There it is. So every time it's going up and down, so let's do it. So it goes tick-tock, tick-tock. It's regular cyclical motion that you could use to measure how much time elapses between one event or another. The reading is up there at the top of this light clock. And what I want to stress at the outset is that this light clock, however unfamiliar it is, right? It is unfamiliar. You cannot go down to Walmart and buy one of these light clocks. But conceptually, a light clock is no different from any other kind of clock, which means any conclusion that we reach about the nature of time that makes use of this light clock as an intermediate part of the reasoning, that conclusion applies to any clock. It would just be harder to reach that conclusion with a clock that had a more complicated internal mechanism. Because, as I'll show you in a moment, the beauty of the light clock is that because the mechanism, the tick-tock mechanism, is so simple, we can very easily determine the effect of motion on the passage of time. Okay, so to do that, I'm going to want to introduce a second one of these light clocks, because I'm going to want to compare the rate at which time elapses on one compared with the other, not when they are stationary, as they are here, but I'm going to want to set one of them into motion. Actually, before I do that, let me tell you what you're going to see, just to prepare you, because this is a great, wonderful result that we're going to find, and I want you to be fully prepared for when it comes. Imagine in your mind that I have one of these light clocks, okay? And I'm going to walk with it. Now it's in motion. From your perspective, think about the trajectory that the light will travel, right? From your perspective, the light will start here, it hits the top of the mirror here, and then it hits the bottom mirror here. So from your perspective, the light will have undergone a diagonal up and a diagonal down trajectory as I'm walking with the light clock. So I'll show you this in a moment, but let me just address one quick question. First, you might think, well, if you're walking with this light clock with the two mirrors, won't the ball of light sort of miss the top mirror because you're moving as you're going along? Answer, absolutely not. What's the argument? The argument is simply this. From my perspective, okay, I'm undergoing constant velocity motion, right? Same speed in a fixed direction, which means, from my view, I can say that I am stationary, and it's you and the rest of the world that are rushing by me. And therefore, from my perspective, it has to be that the ball of light just goes up and down and up and down. Because in my view, I'm not moving. So the ball of light has to hit the top mirror. And if it hits the top mirror from my view, it has to hit the top mirror from your view too. The ball of light cannot, therefore, fly out into space. So what therefore would happen is this. Let's put these two clocks over to the side, and let's look at that ball of light undergoing its motion in the moving clock. Diagonal trajectory up and down. Now notice something. The amount of time that passes on the two clocks is different. Why is that? Well, think about it. Look at the trajectory of the light in the moving clock. Because it's a double diagonal going up and down on the diagonal, the trajectory that it follows for it to go tick and tock, and let me show you this in slow-mo, the trajectory that it follows to go tick and tock is longer, right? So let's take a look at that. Set these guys into motion. This guy has already gone up and down. He registers 1. This guy, because he's going on a longer trajectory from your perspective, and yet the speed of light is constant, longer trajectory, it's going to take it longer to get there, which means this guy's gone tick-tock. This guy has yet to reach the top of the mirror. So if we let this guy continue on, then notice that this guy is reached 2. This guy is just bouncing off the bottom. He's far away from reaching 2. Let him keep on going, and so on and so forth. You see that the rate at which you've got time elapsing on the moving clock is slower than the rate at which time elapses on your stationary clock. And it all comes down to the speed of light being constant. The perspective, that is, from the laboratory observers, those folks who are watching the moving clock rush by, they see that the ball of light in the moving clock is still going, bouncing up and down between the two mirrors, but from the perspective of those of us in the laboratory, the trajectory which the light needs to follow to go tick-tock in the moving clock, the trajectory, the path is longer because it's going along this double diagonal trajectory from our perspective. And if the path is longer, but the speed of light is the same, that means that the tick-tocks happen at a slower rate in the moving clock. Our clock's going tick-tock, tick-tock. The moving clock is going tick-tock, tick-tock. Time itself is elapsing slower on the moving clock. So this is this wonderfully amazing idea that we have now established with this light clock, that from the perspective of those in the laboratory watching a moving clock, they will conclude that time runs slowly on that moving clock. And again, I've used the light clock as a tool, as an intermediate step, because as we just saw, I can easily see the effect of motion on the passage of time. The same would be true if I used any other clock, a Rolex, a grandfather clock, because what we're talking about is how motion affects time itself. And the conclusion is that from our stationary perspective, a clock that's in motion will tick off time at a slower rate. We now know that time elapses more slowly on a clock that is moving relative to you. And we're going to shortly calculate the rate at which that moving clock ticks off time compared to your clock. But first, I want to address two vital questions to this issue of the slowing of time. And the first is, if you are moving with that moving clock and someone on the platform watching you says that your clock is ticking off time more slowly, do you feel that time is elapsing more slowly? And the answer to that is absolutely no. You don't, because again, it goes back to that very same point that I stressed at the outset, right? When we had, say, George and Gracie out there in space. So they're out there in space and they were passing each other, and I emphasized that each could claim to be at rest and that the other is moving by them, right? So that very same idea here, we're only talking about constant velocity motion, fixed speed in a fixed direction, that tells us that the person that you see moving with that moving clock, that person can claim that they are at rest, and it's you that's moving. So from their perspective, time is elapsing as it always does. If you will, the light clock relative to them is going up and down, just as it always does. You and the rest of the world are rushing by them. So, bottom line is, nobody actually feels internally that time is ticking off more slowly because of the fact that everybody can claim to be the person, the clock, at rest. Okay, now, that being said, if indeed you are watching a clock that relative to you is moving, you should see that time on it is elapsing more slowly if you're not moving with that clock. So the question then is, why don't we ever notice that time ticks off slowly on a clock that's moving relative to us? Why did it take the genius of Einstein to figure this out? Why don't we know this in our bones? Why don't we experience this in everyday life? And the answer to that is the same answer that we've come to in analogous questions that we've encountered earlier. It all has to do with the fact that everyday experience only taps into a small little part of how the world is configured. And in this particular case, everyday experience does not involve us watching objects that attain speeds near the speed of light, which is where these effects kick in maximally. So let me just give you a little demonstration where you can see that idea in action. So this here is, if you will, your very own light clock that you can play with on your own. And what you do with this light clock is you set the velocity of the clock at whatever value you want, and it's all in fractions of the speed of light. Good. Okay. Now, if you set the speed of the clock to be relatively small, non-zero but relatively small, let's look at the rate of ticking on that clock compared to what it would be doing if the clock were not moving at all. And notice that the diagonal path here has hardly any diagonal to it at all, because the speed of the clock is so slow compared to the speed of light that light goes up and down with virtually no ability for the clock to move to the right during any of the tick-tocks. So the motion of the clock has very little effect on the passage of time when the speeds are slow. But when the speeds pick up, let's do another version of this. Let's put the speed, I don't know, 60% or so of the speed of light. Now, the clock can move significantly between its tick-tock because it's going quickly. It's going at a speed on par with the speed of light, half the speed of light, a little bit more. And now the diagonals truly are longer than the straight up and down. And just to emphasize that point maximally in this little demonstration, again, play with this. Here we are at 99.9% of the speed of light. So if I now turn this fella on here, wow, look at that. Look how far. It didn't even get to do its first tick of tick-tock. That's how fast this clock was moving relative to the speed of light. So whereas when it's stationary, it would go tick-tock, this one went tick. Didn't even get to the k of tick. That's how far this clock moved to the left because of its very high speed. So this clearly shows us that, again, it is the speed of the clock which determines the rate at which time on it will tick off more slowly than on a clock that is stationary. That's the key point. But we want to go further, because ultimately what we really want to do is to derive a formula for how much slower time ticks off on a moving clock compared to a stationary one. And I'll derive that mathematically for those of you who are taking the math version of this course in the next section. But let me give you the essential idea here. And what is the essential idea? Well, the essential idea can be gotten by a little bit of analysis on one of these moving light clocks. So here is our little schematic version of a light clock that's in motion. And if you think about the process of going tick-tock, based on what we've described in that little demonstration that we just did, the key thing to think about in order to know how quickly this clock will go tick-tock is to look at the length of the trajectory. So the light, little photon, if you will, starts here, and in order to go tick, it has to travel that journey, and to go tock, it has to travel that journey. And since the speed of light is constant, what is most relevant here is how long that journey is relative to how long that journey would be for the stationary clock. And for the stationary clock, it just goes up and down. So if I just mark that for good measure, let's give that guy a different color. Let's call this guy blue. So if this length over here is, say, equal to L, and this length over here is equal to D, then this one will be D as well. So this guy, to go tick-tock, the stationary one, it goes up and down. So it goes L plus L. It goes 2L to go tick-tock on the stationary clock. And on the moving, to go tick-tock, it's D plus D equals 2D. Now, again, since the speed of light is constant, this is telling us that the duration for each tick-tock on the moving clock, let's compare that with the duration for this guy to go tick-tock on the stationary. So that's the duration of tick-tock on the moving compared to the duration for tick-tock on the stationary clock. Well, that ratio is just the ratio of the distances, because the speed of light is the same. So that's 2D over 2L, which is D over L. So that is the essence of the issue. Tick-tock on the moving clock compared to tick-tock on the stationary clock is the ratio of the length of the trajectory in the moving clock from our perspective watching it compared to the length of the trajectory on the stationary clock. So that is the key formula describing the rate at which the tick-tocks happen on the two clocks. But now let me just take this a little bit further and note the following point, which easily can get confusing. It's a very simple point, so if ever you find yourself confused in this, calm down, take a deep breath, think it through, and you'll be able to work it out, which is this. If you're considering the amount of time that elapses between two events, right? If you're measuring the elapsed time between two events on any clock, but in particular on a light clock, you want to know the number of tick-tocks. That tells you how much time has gone by. Now, if the duration for each tick-tock is longer, then less time will elapse on that clock. Longer tick-tocks, tick-tock, means less time will elapse. So what that means is, if we are looking at not the duration of tick-tocks, but the elapsed time. So the elapsed time on, and I'll fill in which clock in a minute, divided by the elapsed time here. And I'll fill in the clocks right now. So if the duration of the tick-tock on a moving clock compared to the duration of tick-tock on a stationary clock, let's say this is a ratio of 5:1. That means that 5 times more time will elapse on the stationary clock, where the tick-tocks are faster, compared to the amount of time that elapses on the moving clock. So then this translates into the elapsed time on the stationary clock compared to the elapsed time on the moving. These are inversely related to the duration of the tick-tocks. This is equal to D over L. So again, if this length here is 5 times the length for the ball to go up and down, the ball of light to go up and down in the stationary clock, then that means the tick-tocks are happening 5 times as slow in the moving clock, which means 5 times more time will elapse on the stationary clock compared to the moving clock, because the tick-tocks are happening faster over here. So that means that we can now take the little formula that we have indicated over here and translate that into the elapsed time in the stationary clock to the elapsed time in the moving clock is the ratio of the length of that diagonal that we have over here to the length of the straight up and down. So now we've basically reduced the calculation of how much time slows on the moving clock compared to a stationary clock to really a bit of geometry and trigonometry. And I'll show you how that goes if you're taking the math version in the next section, but let me give you the answer. Here is the answer that we will establish. If this clock that we are looking at over here let's say this guy has a velocity that's heading over this way, and this velocity is equal to v. Then that formula takes the speed v as input and tells us how much slower time elapses on the moving clock compared to the stationary clock. Now, for those not taking the math version of this course, this is one of only two equations I'm going to show you. The other, of course, being E equals mc squared. But this formula is just as important as E equals mc squared, not quite as famous, but it tells us that the time that elapses on a moving clock is slow relative to that on a stationary clock by a factor of 1 over the square root of 1 minus v over c squared. This expression, this little formula, is so important, we give it its own name. We call it gamma. Again, we'll derive that in the next section, but I just want you to get a bit of a feel for this result before we do that. We are going to look at two clocks, and one clock you can imagine is here on Earth, which we will call the stationary one. One clock is on a rocket ship, so now we've gone from a train to a rocket ship because we want some of these speeds to be able to be really fast. And what this demonstration will do, it simply takes the formula that I have told you that we will derive in just a moment. So just remember what that formula is. So this is equal to, we claim, 1 over the square root of 1 minus v over c squared. The demonstration will take the v that you input into the demonstration, calculate that, and show us the amount of time that elapses on the rocket compared to the amount of time that elapses on Earth. Okay, let's do that. All right, so let's be conservative at first. I've chosen the speed of the rocket ship to be 12% of the speed of light. Set this guy in motion, and you can begin to see a bit of a time difference between them. It's hard to see, but there is a bit of a difference. But now let's crank this up, and let's go to 67% of the speed of light. And now you really can begin to see that the elapsed time on the rocket ship is less from the perspective of those of us here on Earth looking at our stationary clock. And let's then be inspired, and you should do this on your own, again, to feel the formula, this formula for this object called gamma in your bones. I'm now at 95, I don't know, let me push it all the way. Let's go to 98.5% of the speed of light. And now you really begin to see the difference between these two. It's dramatic. Here we are on Earth, and hour after hour is going by in the usual way, but from our view, that clock in motion, time is ticking off very, very slowly. So this factor, this guy called gamma, this time dilation, as we call it, kicks in substantially for speeds near the speed of light. At everyday speeds, time dilation is still there, right? So this guy over here, where the velocity is in the denominator, that kicks in at any velocity, right? But that number is so close to 1 for pedestrian everyday speeds that we don't notice it. So clocks move around the world all the time. We don't notice that they're ticking off time at a different rate, only because that formula is such that gamma is very, very close to 1. So the ratio of time on the moving clock to time on the stationary is virtually indistinguishable from being equal to one another. But the effect is there nevertheless. Having said that, let me just emphasize one little loophole that we will come back to. It's kind of a curious loophole, which is that if you have individuals that are moving at relatively slow speeds, but they're very, very, very far apart, then that can amplify this effect. So there can be big differences in time, even at slow speeds, if you're talking about observers that are very far apart in space. We will come back to that and its curious implications as we go forward. But putting that to the side, if you're talking about observers that are reasonable distances apart, distances that might be planetary scales or even galactic scales. It's only when they're moving relative to one another very quickly that this time dilation effect kicks in substantially, but it is there all the time. So in some sense, we all carry our own time. This completely shatters the oneness of time that Newton envisioned, right? Newton envisioned that there's one clock out there in the cosmos, ticking off second after second after second, the same for all of us. This shows directly that that's not true. We each carry our own clock, and our clock ticks off time at a rate compared to others that depends on the relative speed between us. I have been talking as though time dilation is an established fact regarding how time itself behaves. And there's good reason for that, right? We came to this idea of time dilation based upon an experimental fact that the speed of light is constant. And then following in the footsteps of Einstein, we have parlayed that into an understanding that time on a moving clock ticks off more slowly than on a stationary clock. Good, okay, all that's fine. But you know, when you're talking about an idea that is as strange, that is as counter to experience as time dilation, well, you just are happier. You just are more convinced if you have some direct experimental support for that idea. So the question is there some direct experimental support for time dilation? And there is. There is a lot of experimental support. I'm just going to give you two little examples that really help solidify the idea that this really is tapping into the true nature of time. Okay, the first example is, look, the most flat-footed, straightforward way of verifying that time on a moving clock slows down. It is an experiment that was undertaken in the 1970s, and what happened in this experiment is very straightforward. Scientists took two atomic clocks. They put one of those clocks on an aircraft, and the other atomic clock they left back on the tarmac. They flew this plane all around the world, and they then landed the plane, ultimately, and compared the amount of time on the moving clock to the amount of time on the stationary clock. And lo and behold, when they compared the two clocks, they found that different amounts of time had elapsed on each. In fact, the time difference between them is exactly what Einstein's ideas predict. It's a touch more complicated to work it out relative to the formula that we have derived here. The formula that we derived, this gamma factor, plays a part in the analysis, but because this plane is flying around, it's not at constant velocity, gravity comes into the story. It's a little more complicated, but it absolutely establishes very directly that time on moving clocks ticks off at a different rate. And when you undertake the detailed analysis, taking account of all of the complexities that we're not going to talk about, it confirms all of the ideas that we have described. So that is, look, once you see that these two clocks show a different amount of elapsed time, you, I would think, should be convinced that these ideas are correct. But nevertheless, let me give you one other piece of experimental evidence that's sort of fun, and we're going to come back to it in a little while. It has to do with a species of particles called muons. You don't need to know what muons are, but they're very much like electrons. They're a little bit heavier. But the essential feature of muons is that they're unstable, which means that they disintegrate. They fall apart in a fraction of a second, which means that when these particles are produced, as they are in the upper atmosphere, they can drop down toward Earth, but at some point in the journey, the particle disintegrates. It falls apart into other particles. It breaks apart in essence. And the question is, how far can the particle travel before that disintegration kicks in? And that's worth studying for a moment. So the particle starts up here and drops all the way down to there. And the issue is, how far can it travel before it breaks apart? Now, you all know what the answer to that is. It must be the case that the distance it travels is equal to the velocity times the time. And this time here is its lifetime, right? How long it lives before it disintegrates, before it falls apart into other particles. Now, in the laboratory, scientists have measured the lifetime of these muons, and it turns out that the answer is 2.2 times 10 to the minus 6 seconds. And since scientists also know the velocity that these muons have in the upper atmosphere as they're coming down, they know how far they should be able to travel. And here is the remarkable thing. When you do that calculation, you find that the muon, you would think, should only have enough time before it explodes to go about that far. But observations show that the muon goes much further. What's the explanation? Well, let's think about time for a moment, because this is the time as measured in the laboratory. The muon is in motion, right? That means that its clock is ticking off time more slowly, which means that the muon, from our view, its clock is ticking off time slowly, so it should be gamma times delta t as measured in the laboratory when it's at rest. The way to think about this is, it's as if the muon, if you don't mind me putting it in slightly violent language, the muon has a gun to its head, right? And when a clock that the muon is carrying ticks off 2.2 times 10 to the minus 6 seconds, it pulls the trigger and it falls apart. But if the muon is in motion, from our view, its clock is ticking off time more slowly. So our watch will have long since gone by 2.2 times 10 to the minus 6 seconds, and the muon still will not have pulled the trigger, because from its view, that amount of time has not yet elapsed. So what this means is that the distance, d, that the muon should be able to travel, taking this time dilation into account, is now v times 2.2 times 10 to the minus 6 seconds, its lifetime when at rest, multiplied by gamma. So the formula then is 2.2 times 10 to the minus 6 seconds times v divided by square root of 1 minus v over c squared. And it's that formula. This number is bigger than just the product of the two things in the numerator. This fella over here makes it larger. That explains that the muon can go all the way from here to here without disintegrating. So let's get a feel for this result, that muons travel further than you would have thought based upon Newtonian reasoning because of this time dilation factor. So this little demo, what you do here is you can choose the speed of the muon there in the upper atmosphere. And this will show how far the muon travels before it disintegrates. So again, at slow speeds, not much of a difference from Newton, but then it really kicks in with a vengeance at high speeds. And in fact, this one lets you show the Newtonian answer. So that dotted line that you have on the bottom there, if you can see it, it'll be easier for you to see it on your own when you play with this. So this dotted line is how far Newton would say the muons will be able to travel before they disintegrate. So that's just 2.2 times 10 to the minus 6 times their velocity. But then if you take time dilation into account, you see that the muons can travel much, much further. And that's how we can explain how they can reach from the upper atmosphere down to the surface of the Earth, where Newton would have thought they would have disintegrated way before they hit Earth's surface. So that gives us two strong pieces of experimental evidence that time dilation is real, straightforward, direct experiments that can really only be explained by this idea that moving clocks tick off time slowly. There's a wonderfully startling implication of time dilation that isn't often as fully emphasized as it might. And I'd like to briefly describe it to you now. It has to do with the following fact. So we know from the formula for gamma that the effects of time dilation only really kick in a significant way when the relative velocity that's being studied in a given situation approaches the speed of light. That's all true. But there is another way in which the effects of time dilation, in which the effects of the relativity of simultaneity, in fact, can be amplified over very large distances. Over very large distances, these effects can become significant even when the speeds involved are ordinary, everyday velocities. So how does this go? Well, to set it up, let's first think about time for a moment from the perspective of experience, right? So we all generally think of time as a kind of continuous unfolding, a continuous flow. But for the purpose at hand, it's useful to also think about time in a different way, as a kind of series of moments, a series of snapshots, one moment after another moment after another moment. And any physical process can, of course, be described in this way. A flower, a wild animal running moment after moment after moment, horse running and so forth. It's just a series of snapshots that capture each subsequent moment in time. In fact, you can even go out into space, if you will, and think about the Earth in its orbit around the sun. Again, moment after moment after moment. Okay, so what I'd like to do is start with that way of thinking about things, and I'd like to compare my set of snapshots, my sequence of events that are unfolding over time, and want to compare my snapshots to somebody else's snapshots who's moving relative to me. And to do that, there's a related idea that I want to introduce, which is the concept of a now slice. And by a now slice, what I mean is I consider the world and I think about all things that are happening right now, like the stroke of 12 on a clock, or at that moment, my cat jumping, or perhaps other events like a bird taking flight at this very moment, say in Venice, or we can go cosmic on this too. So we can imagine at that very moment, a meteor just striking the surface of the moon, or go even further away, we can imagine a supernova explosion way in the far reaches of our galaxy. Now, a now slice is a slice in this picture here where I put down all those events which I say happen at one moment in time. And if I look at one now slice after another, this is the unfolding of one moment after another after another. So each of those events that lie on a given slice constitute those things that I say were real, were happening at a given moment. One now after another now after another now. There are 2 points that I want to stress about this. We give this picture a name that makes perfectly good sense. We call this space-time, right? Because we have all of space in each one of these slices. Imagine the slice goes on forever, includes everything that's out there in the cosmos at a given moment. And along this direction, of course, we have the unfolding of time. So we have space and time. That's where the name comes from. Second point is common sense and everyday experience would tell us that every single observer in the universe, regardless of their motion, should agree on what is on a given now slice. That's the Newtonian view of how the world is put together. But when Einstein comes into the story, that radically changes. Because with Einstein, we have now learned that the constant speed of light means that observers who are in relative motion do not have the same sense of simultaneity. They do not agree on what is happening at a given moment in time. And that has a startling implication that I'd like to describe. And to do that, let me use a little metaphor here. It's one that actually I used in my NOVA program, Fabric of the Cosmos, if you've seen that. But if not, it's a straightforward metaphor. Think about this whole expanse, this whole space-time expanse, as if it's kind of like a big cosmic loaf of bread. And what these now slices are, I'm basically cutting this loaf of space-time into pieces which represent all of space at a single moment in time from my perspective. If someone is moving relative to me, they have a different perspective of what now is, what is simultaneous, and that means they carve up the loaf at a different angle from me. So let me just show you that schematically. So let me imagine I consider the bird's eye view of that picture just because it's easier for me to draw. And let me write down my now slices in there. So from the bird's eye view, I will draw space at one moment of time, space at, say, the next moment in time, the next moment in time, and so forth. So these are all my now slices. And just so that I have these labeled in a way that we all understand, put it down here. Going to the right in this picture is what I consider the future. And going this direction is what I consider the past. Now, somebody is moving relative to me, and let's say they are also interested in drawing space-time slices. So let's draw theirs. And because they're moving relative to me, they will slice up this region of space-time at, say, a different angle relative to me. They slice the loaf with a knife that's angled relative to my slice, because their notion of simultaneity, what's happening at a given moment, say, differs from mine. Now, if we are dealing, and this is the point, if we are dealing with low velocities, the person far away has a low velocity, so we're not talking about velocities near the speed of light. What that translates to in this picture is that the angle that we have here, this angle is relatively small. So in the vicinity of where that person is sitting, low velocity motion has virtually no impact. But the point, and I'll show you an animation of this in a moment, is that over larger and larger distances, let's say I am over here, and let's say somebody else who's doing the moving is far away, over very large distances, a tiny angle can get amplified into a very large difference in time, a very large difference in our conception of what's happening at a given moment. So let's take a look at that idea in animated form. Let's imagine we are looking at a big expanse of space and time, and we have a character, an alien, very, very far away in space, and we have a more familiar looking character, a human being sitting still on a bench over here. Now, if initially these two individuals are not moving relative to one another, they share the same idea of simultaneity if there's no motion, so they slice through the space-time loaf in the same way. They both agree on what's happening at a given moment in time. Okay, but now let's change things a little bit. Let's let our alien friend hop on an alien bicycle, say, and let's say the alien starts to ride away from me. Because of the relative motion between the alien and me, or the guy on the bench, the alien has a different conception of simultaneity, a different notion of what's happening now. And what that means is, when the alien slices up the space-time loaf into all of space at a given moment, the now slice will cut through at a different angle. And again, the point is, small velocity means small angle, but consider a small angle over larger and larger and larger distances between us, and that small angle turns into a big change in time. So in fact, the alien's now slice actually sweeps into the past. And it can be a significant sweeping into the past. When you put in some numbers, as we'll do later on in this course, you find that the sweep goes beyond when that guy was a baby, goes further back in time than that, and in terms of events on Earth that the alien would claim to be happening right now from his perspective, it might be hundreds of years ago. Say, Beethoven putting the final touches on the Fifth Symphony. Now, the thing that's not completely obvious about this and does take some mathematics, and if you're taking the math version of this course, we will do the math. If you're not taking the math version, I hope this is sufficiently exciting that you might take the math version of the course. But putting that to the side, why did it swing to the past and not, say, to the future? Here's a quick way of thinking about it. Remember the treaty signing ceremony. President of Backward Land, right? Backward Land was rushing away, that president, and he signed the treaty late, right? He was not the one who did it first, he did it second, if you recall. So in essence, if you are moving away, you are sweeping to the past. You are old news from that perspective. But that also means, thinking now from the treaty perspective, the president of Forward Land, if you are approaching, if you're going forward, your notion of simultaneity should sweep into the future, and indeed that is the case. So if the alien hops on the bike again, but turns around, say, and doesn't ride away from Earth, but rides toward the Earth, then indeed the alien's notion of what's happening right now on Earth does sweep from what we consider to be the present into what we consider to be the future, and might include strange things from our perspective, like this guy's great-great-great-granddaughter maybe teleporting from one place in the universe to another. So the point is, the whole notion of what you consider to be real, what you consider to be taking place right now, is totally dependent on your motion, right? So initially, when the alien was not moving, say, relative to us, let's put ourselves in the position of the guy on the bench. From our view, we agree with whatever the alien says is happening right now, whatever's real, we totally agree, right? Now, when the alien gets on a bike, we don't suddenly discount the alien's perspective because he's on a bike. So if the alien then says that other events are considered to be now, to be real on his now slice at a given moment, we should accord that statement the same status, the same believability as when the alien wasn't moving relative to us. So if the alien tells us that things in our distant past are real, they are on his now slice at a given moment, we need to take that into our perspective on what's real. If the alien tells us that things in our future are on his now slice at a given moment, we need to take that into account too. So what this collectively tells us is that the traditional way that we think about reality, the present is real, the past is gone, the future is yet to be, that is without any real basis in physics. What we're really learning from these ideas is that the past, the present, and the future are all equally real. Time dilation is one of the strangest counterintuitive concepts that you're ever really going to encounter. And it's nice to have a kind of mental mnemonic, a kind of shorthand way of thinking about this strange idea that perhaps makes it a little bit more intuitive. I'd like to give you such an intuitive way of thinking about time dilation now. And let me say, you can justify the explanation I'm about to give you mathematically. And if you're taking the mathematical version of this course, we will justify it a little bit later on. But if you're not, don't worry about it. But this gives you a nice way of thinking about why it is that time ticks off more slowly when a clock is in motion. Here's the idea. Forget about time for a moment. Let's just think about space. And imagine that we have a car that's headed due north at 100 kilometers per hour. Now imagine that the car steers off and drives to the east without changing its speed. Now its motion in the northward direction will not be as quick as it was previously because some of the northward motion has been diverted into northeast motion. So what that means is motion can be shared between dimensions, and when motion is shared in that way, motion that was fully devoted to one direction gets diverted to another direction, so motion in the initial direction slows down. Let me just show you a little visual on that. So here we have our car. I'm going to show three versions of the car. One's going due north, the others are going northeast at various angles. And there you see the point. This car has traveled much further in the northward direction than these cars because these cars have diverted some of the northward motion into eastward motion. So the idea is when you go in a different direction through space, you divert some of your initial motion into that new motion in the new direction. Good. Okay, now let's take that idea and apply it not to space, but to space and time. Okay? So right now, here I am, and you would say that I'm not moving relative to you, say. But of course I am moving, right? Look at my watch, right? My watch is ticking second after second after second, taking me forward in time, forward in the time dimension, if you will. Good. Now, imagine that I get up and I start to walk. Einstein basically told us that as I walk, I divert some of my previous motion through time into this motion through space, which means I move through time less quickly. Much as over here, this car goes less quickly in the northward direction because it's diverted some of the initial north motion into east motion. When I start to move, I divert my initial motion through time into this motion through space, so my passage through time slows down. That idea, to me, is the most straightforward, intuitive way of understanding time dilation. You can make it mathematically precise, but putting that to the side, if you want to think about why it is that a clock slows when it's in motion, simply think to yourself, when it's sitting still, all of its motions through time, when I see it moving through space, it has diverted some of that motion through time into motion through space, so it passes through time more slowly. That's why time ticks off slower on a moving clock. The constancy of the speed of light we've seen in the context of all of the ideas of special relativity has a dramatic impact on our understanding of time. It also turns out, remarkably, that the constant speed of light has a dramatic effect on space and also on mass. And we're going to talk about both of those, but for now, let's turn to the first one, the implications of the constant speed of light for our understanding of space. So first is, why would we expect motion to affect space? Well, it's pretty straightforward, right? Because speed, as we emphasized, is distance divided by duration, which of course is space divided by time. So if we learn, as we have, that the speed of light is constant, well, we've also learned that time is not constant. So that means that space must in some way compensate for the non-constant aspects of time in order that their ratio stays the same, allowing the speed of light to be unchanged. So in schematic language, in order to ensure that the speed of light is constant, space must adjust itself in tandem with time so that the ratio for light stays fixed. So the picture you should have in mind is something like this. If we consider that time is not constant, therefore space must change too in relation to motion, so that the ratio space over time is such that the speed of light can remain unchanged. And what we'd like to do is take that rough idea and make it explicit. We'd like to now determine what the effect of motion is on space. How are we going to do that? Well, let's work in the context of a concrete example. Let's imagine that we have a train, and we want to ask ourselves, how would you measure the length of a train? Well, that's a pretty straightforward thing to do when the train is stationary, right? Because if the train is stationary, you take out a tape measure and you measure the length of the train, right? So let's get things going. Let's imagine that that is the situation, and we're going to consider the length of a train from the perspective of somebody on the train. So that will be our fearless train rider, George. From his view, the train is at rest relative to him, so he pulls out his tape measure and he simply stretches it from one end of the train to the other, and that way he measures the length of the train, and let's say he finds that the train is 210 meters long. Good. Okay, that's all perfectly straightforward. Let's now imagine that our second character, Gracie, she is on the platform. So from her view, the train is in motion. So she has to use another approach to measure the length of the train, right? She can't really pull out her tape measure and measure the length of the train because the train's rushing by, right? So that's not a way that she's going to measure the train's length. Instead, she does something more clever. Let's assume that she knows the train's speed. Let's also assume that she has a stopwatch. What she can do is the following. She'll start the stopwatch just as the front of the train is passing her. She will stop the watch as the rear of the train passes her. So she knows how long it took for the train to pass by her. She knows the speed of the train, and she simply multiplies them together. She multiplies velocity times time to get the length of the train, right? So let's see her do that. There she is on the platform. She has her stopwatch handy. The front of the train goes by. Boom, she starts the watch going. When the rear of the train passes her, boom, she stops the watch. She gets the elapsed time, in this case 5.9 seconds. She multiplies it by the known speed of the train in order to get the train's length. That's her approach. Now here is the remarkable fact. The two approaches, George's approach, where he simply used a tape measure, Gracie's approach, where she uses this watch and the known speed of the train, they yield different answers, right? So if you multiply this out, just in this particular example, 30 times 5.9, 177 meters. Numbers, I should say, which I've made up just to illustrate the point, which is that Gracie has gotten a shorter length of the train compared to George. Now, at first sight, that is hugely surprising, right? But the question is, does this actually puzzle George? Assuming that George has taken the discussion that we've already had to heart, and he fully knows about time dilation. With the notion of time dilation, does the discrepancy in the length of the train from his perspective and from Gracie's perspective, does it puzzle him? And the answer is no. Because from George's perspective, here's what he says. He says, look, I understand Gracie's approach. She's using length equals speed or velocity times elapsed time. But I also know that Gracie, from my perspective, right? I'm now George. Gracie, from my perspective, is in motion. Clocks in motion tick off time at a slower rate. If a clock is ticking off time at a slower rate, it'll show less elapsed time, and therefore it will, in that multiplication, yield a shorter length. So from that point of view, George understands why it is that Gracie got a shorter length, but the question remains, who is right? Is the length of the train 210 meters, as George says that it is, Or is the length of the train 177 meters, as Gracie says that it is? Now, you can probably guess the answer to the question of who is right based on what we have discussed so far. The answer is they are both right. The answer is length itself is a concept that we need to rethink. We normally think about length as the length of an object, but in fact, the length of an object depends on its speed when you measure it. Now, where does that idea really come from? That idea comes from the following fact that we have emphasized repeatedly. Simultaneity is in the eye of the beholder, right? Now, to measure the length of an object, you need to measure its front and its rear simultaneously at the same moment. Now, if two observers have different notions of simultaneity, they will therefore have a different notion of the length of an object. No single result is solely right. No result is wrong. They're all equally good. Now, having said that, just a little bit of language. We generally call the length of an object, when you measure it when you are at rest relative to the object, as George is in the case of the train, we call that the rest length of the train. We call it the proper length of the train, but that just calls out a particular perspective, the perspective of somebody not moving relative to the object. But fundamentally, you can measure the length of an object when it has any speed relative to you, and you will get a different answer depending upon the speed of the object. So the general conclusion then that we are reaching is that moving objects are shortened along the direction of their motion. And let me stress that it's only along the direction of motion that the object will appear shorter. The height of the object will not change at all. And a little tiny argument can establish that. For instance, if you were to imagine that the train were going into a tunnel, right? And let's say it just barely fits. Now, if it were the case that from one person's perspective, the height of an object, not in the direction of motion, if that were to change, let's say I were to say that the height of objects gets smaller. Well, then from my perspective on the train, the tunnel will be smaller. I won't be able to fit. I should smash into it, right? From the perspective of someone who's on the tunnel, it'll be the train that will be shrunk in that direction, and so it will fit. Now, however weird relativity is, it can't be the case that in one person's perspective, there's a crash of the train into a tunnel, and from another person's perspective, there's not a crash. That would really be a contradiction. That would be a paradox. That can't happen, and therefore we learn that it can't be the case that dimensions that are perpendicular to the direction of motion, they are not changed at all. They stay fixed. And so we describe the shortening of an object along the direction of motion. We call that length contraction, or we call that Lorentz contraction. That is the language that we used, and let's take a look at a simple example of that. So here is a case where we're looking at a New York City taxi cab moving pretty quickly along, and along the direction of motion, the taxi cab is shrunken. It is shorter along that direction than it would be when it is at rest. So let's take a look at a demonstration which will give you a feel for the amount by which an object appears shrunken along its direction of motion when you are looking at it. So this little demonstration here allows you to pick the speed of this taxi cab as it's rushing by you. And again, get a feel for this in your bones. As the speed creeps up, not much of an effect on its length, but when the speed approaches the speed of light, the object gets ever shortened along the direction of motion. Now, you can ask yourself a natural question at this stage, which is, does the object in motion really shrink And if it does, like, what's the force that's squeezing on it? Now, that's a natural question, but it's pretty loosely phrased, because the main point that we have come to is that the notion of length itself requires a notion of simultaneity, because again, if you're measuring the length of an object in motion, if you first say measure the back of the object and the object moves and then you measure its front, let's say I'm measuring the length of a fish in a pond, right? If it's swimming along and I first measure its tail and I let the fish swim and then I measure its nose, well, I'll get a different length than I would if I measured the front and the back, the nose and the tail at the same moment. So it's critical in talking about the length of an object to commit to a notion of simultaneity, and that requires choosing a frame of reference, because observers in motion don't agree on what happens at the same moment in time. And because of that, different vantage points differ regarding what happens at the same moment. We come to the conclusion that an object in motion has a length that depends upon its speed, because its speed determines the degree of the lack of simultaneity between two perspectives. So if we ask the question again, do objects in motion shrink? The best answer I can give you is yes and no. It definitely is the case that an object in motion has a length from my perspective that is shorter than when that object is at rest. But it's not as though someone has come in with a vice and crushed the object down. It simply is that the old idea that there's a universal notion of the length of an object needs to be updated. By relativity, the length of an object depends upon its speed when you measure it. And that is a surprising result. The length of an object depends on its speed. Now, give you a couple other little examples of that to have in mind. And both of these examples make use of the idea that we discussed earlier, the relationship between observing something and measuring something. So back then, I described how we're mostly focused upon reality. So we don't really care so much about human perception. We care more about what happened in the world to be responsible for what we see. But sometimes it's kind of fun to look at what we literally would see if some of the effects of relativity were visible to us. And in this example here, we are now going to look at a taxi cab, but done more precisely. So this is how a rushing taxi cab would literally look if you could see it rushing by at high speed. Notice that the taxi cab appears kind of twisted, right? In the last frames of that little video, we could see the whole back bumper of the taxi cab, even though ordinarily, if a taxi cab was rushing by us, we wouldn't be able to see the whole bumper. We'd only see the part that was nearest to us. The reason for that is a little bit complicated. It makes use of the fact that when we look at something, we are seeing light from the object. Light takes different amounts of time to reach us from different points on a three-dimensional object, because those three-dimensional points are a different distance from our eye. If you take that into account, then that little video gives you a really good sense of what it would be like to literally see an object rushing by near the speed of light. The second example puts us inside the taxi cab itself, shows us what it would be like to look out the window of a taxi cab that's rushing through a city near the speed of light. And as you can see, the world around you, not only does it have the length contraction that we've described, if you take into account the finite light travel time, the differences from one point to another, you see that space has a kind of warped, distorted, curved look. The world around you seems to be curving in around you when your speed approaches the speed of light. So again, if you could find a taxi that could travel near the speed of light, and if you had really good eyes, so you could actually see the world around you as it was rushing by you at very high speed, that is what you would see. So these are some very strange effects that the constant speed of light has on the nature of space, but they all follow directly from the analysis that we've already done with time. So once you know that time has weird features, you know that space must have weird features too, in order that in tandem they can keep the speed of light constant. We understand now the resolution of the pole in the barn paradox, at least qualitatively. Let's now take a look at the numbers, the mathematical details, which will allow us to reconcile these two apparently contradictory perspectives. So what we want to do is to first take a look, say, at the perspective of Team Barn. We know that they say that the pole fits, and what we want to work out is how does Team Pole come to a different conclusion from the perspective of Team Barn? Team Barn is like, I can't understand how they came to this different conclusion. They said the pole doesn't fit. Let's understand mathematically how it is that they resolve that headache, that conundrum. And they do finally understand this claim of Team Pole that it doesn't fit. So to set this up, let's start by considering the perspective of Team Barn. Let's try to figure out how they make sense of the strange conclusion that they hear from Team Pole. And to do that, let's record a little data to begin with. So according to Team Barn, the pole is rushing by at 12/13 the speed of light, pretty fast. And remember that the pole, its rest length, we are told is equal to 15 feet. Okay, good. Now, let's draw a little picture of this so we know what we are talking about. We have the pole. It's rushing along, and it's rushing along in this direction to my left as I face the board, and the speed of this guy is at v equals 12/13 c. Okay, now what does this mean from the perspective of clocks that are being carried by the pole from the barn's perspective, right? So let's imagine that the pole has clocks at the front and the back, and let me draw those for good measure. So let's say we have a clock here, and we have a clock over here. And we know that the clocks from the barn's perspective will not be in sync with one another, right? So if the pole is rushing this way, we know that the leading clocks will lag behind in time. They will be late, right? And let's calculate how far behind this clock is relative to the clock at the rear. And that we know how to calculate the time difference. So the difference between those two clocks, this little formula, we take v times the distance between those two clocks divided by c squared. So plugging in the data that we have at hand, velocity is equal to 12/13c. We've got the distance between those clocks, and again, this formula is the distance as viewed in the frame whose clocks we're discussing. So this will be 15 feet. And since we're using feet, of course, we'll take c to be 1 foot per nanosecond squared. So here we have our answer. 12 times 15 is 180 divided by 13 nanoseconds. And this is about 13.8 nanoseconds. So what that means is when Team Barn looks at these clocks, if, for instance, this clock over here on the right is reading 13.8 nanoseconds, then this clock over here on the left will be 13.8 nanoseconds behind. So it will be reading 0 when this one's reading 13.8 nanoseconds. Now, qualitatively, what does that mean? Qualitatively, that means that according to Team Barn, Team Pole is assessing the location of the rear of the pole before it assesses the location of the front of the pole. That means that the pole moves between when the rear position is assessed and when the front position is assessed, and that's why the front has time to get out of the barn, according to Team Barn. That is why, according to Team Barn, Team pole comes to this weird conclusion that the pole doesn't fit. Now let's make that quantitative. We know that there's this 13.8 nanosecond difference in the reading of the clocks. That is not the time difference according to Team Barn regarding when the front and the rear are assessed, because of course this clock needs to catch up to that one, 13.8 nanoseconds, but it's ticking off time slowly because it's a clock in motion according to Team Barn. So if we calculate gamma in this case, which will allow us to convert that time difference into the time difference according to Team Barn, what is gamma in this case? Well, again, 1 over the square root of 1 minus 12 over 13 squared, and if you work that out, that gives us a nice answer of 13 over 5. So what Team Barn says is you take this 13.8 nanosecond difference in the clock readings and you multiply it by 13 over 5 to figure out how long after the assessment of the rear of the pole will the front of the pole's position be assessed by those in Team Pole. So let's do that. So if we take 13 over 5 times the difference in the clock readings, and let me just write that as 12 over 13c times 15 feet divided by 1 foot per nanosecond, just to get our full answer. So the 13s go away, the 5 goes into 15.3, so this gives us 36 nanoseconds. So according to Team Barn, 36 nanoseconds after the rear of the pole's position is assessed, the front of the pole's position will be assessed by those in Team Pole. How far does the pole move between those two assessments? Well, that's just velocity times time, right? So we have 36 nanoseconds. How fast is this pole traveling? Well, it's going 12/13 c, so that's 12/13 foot per nanosecond using our usual formulation. And therefore, if you just plug in the numbers and calculate this out, you will get 33.23 feet, approximately, is how far the pole is going to move between the assessment of its rear location and the assessment of its front location. So what does this mean? Well, let's draw a couple of pictures to see what this implies for the measurement of the position of the pole. So let's draw a little schematic representation of the barn, and for good measure, let's make some doors so that the pole can get inside of the barn. And now let's look at the motion of the pole from the barn's perspective. So according to the barn folks, Gracie and her friends, they say that the pole fits inside, period, end of story. But they also recognize that the clocks that are attached to the pole are not in sync relative to each other. And they say that the pole people first measure the location of the rear of the pole and only later measure the location of the front. And we've calculated that there's a 36 nanosecond time difference between when the rear and the front are measured, which means the pole moves during that interval. In fact, we've calculated how far it moves. The distance between these two locations, we calculated that as 33.23 feet. So that's how far the pole moves between when the rear of it is measured and when the front of it is measured. So of course the pole doesn't fit inside the barn. During that interval, it travels this distance, so the front of the pole gets outside of the barn. So in this way, Team Barn is able to clear their headache, right? They didn't need any Excedrin, they didn't need any Advil, they just did a little calculation. And in that calculation, they recognize that Team Pole first assesses the rear location and only later assesses the front, and by the time they assess the location of the front, it has slipped outside of the barn. That's how Team Barn explains this weird-sounding conclusion, according to Team Pole, that the pole does not fit inside. So that gives us our nice explanation, according to Team Barn, of the weird conclusion of Team Pole. Good. Now what we want to do is the same kind of analysis, but from the perspective of Team Pole. We want to understand mathematically how it is that Team Pole can explain the observations, the conclusions, the claims of Team Barn that the pole does fit. And we can do really just the same calculation, but it's worth doing a second time. Same essential ideas, but now let's look at this from the perspective of Team Pole and try to understand how Team Pole explains this headache-inducing claim that Team Barn is saying, where the Team Barn says the pole fits. Team Pole says, how could they say that? And we want to understand how they clear that conundrum by analyzing clocks in the Barn frame from their own perspective. And of course, the key idea will be that according to Team Pole, the clocks in the Barn frame of reference are not in sync, even though the Barn folks say that those clocks are in sync, right? So just so we can get a picture of what's going on here, if we draw a little schematic here of the Barn, so the Barn has clocks all along its length. Let's just draw the clock, say, at one end and the other. And according to Team Pole, it is the Barn that is rushing along at a speed v in this direction, and that speed v is equal to 12/13 of the speed of light. And since the Barn is rushing in that direction according to Team Pole, this is then a leading clock. It's in the direction of the motion. Leading clocks lag behind. They are late. So this clock will lag behind this clock. And we can calculate how much it will lag behind in order to understand the reasoning of Team Barn from Team Pole's perspective. So what is the time difference between those clocks? Well, we know what to do. We take the velocity, which is 12/13 c. We multiply it by the distance between the clocks from the perspective of Team Barn. That's the way this formula works. That is 10 feet. And we divide through by c squared, which is just 1 foot per nanosecond in the approximation that we are using. So this gives us 120 divided by 13 nanoseconds. And if you just work that out, that's approximately 9.2 nanosecond difference between these two clocks. And what that means is, according to Team Pole, if, say, this clock is reading 12 noon, then this guy over here will be lagging behind and will be 12 noon minus 9.2 nanoseconds. So qualitatively, what this means is, according to Team Pole, Team Barn is first going to assess the location of the front of the pole. Say they will claim it's inside at 12 noon. And then they will allow some time to elapse before this clock catches up to 12 noon. And in that interval, the Barn will move to the right, allowing the rear of the pole to slip inside. And that's why, according to Team Pole, Team Barn says that the front and the rear of the pole are inside at the same moment, whereas from Team Pole's perspective, those are not the same moment because the clocks in the Barn are not in sync. Now, we can make that quantitative, of course, by figuring out, according to Team Pole, how long will it take for this clock to catch up to 12 noon? It's not 9.2 nanoseconds because clocks in the Barn frame of reference are ticking off time slowly, according to Team Pole. So we have to multiply that 9.2 nanoseconds by gamma to get the amount of time that will elapse, according to Team Pole, between when those two clocks, when I should say this clock catches up to 12 noon. So let's do that. What is gamma? Gamma is 1 over the square root of 1 minus 12 over 13 squared. 1 minus v over c squared. Work that out. That is 13 over 5. So now, if you allow me, I'm just going to take that 13/5 and multiply it by the time difference that we calculated above. So if you don't mind, I'm just going to do it right over here. 13/5 times 120/13. 13's cancel. 5 into 120, 24. So that gives us 24 nanoseconds. So again, according to Team Pohl, the assessment of the front and the rear of the pole happened 24 nanoseconds apart. That is, this clock and this clock differ from one another, and it takes 24 nanoseconds for this clock to catch up to 12 noon. Now, in that interval, the barn is moving over to the right. How far does it move? Well, that's just velocity times time. So we have 12/13c, so let's do that, 1213 feet per nanosecond, multiplied by that 24 nanosecond time difference. And if you just calculate that out, it comes to about approximately 22.2 feet. So according to Team Pohl, the barn is moving 22.2 feet between the measurements of whether the front and rear of the pole are inside. Namely, more precisely, it is moving 22.2 feet between when this clock and this clock have the same reading. So we can see what that implies by drawing a diagram similar to the one that we had over here. But now this is from the perspective of Team Pohl. Let's draw a version of the barn. And let me, as before, give some doors for this pole to come inside. And from the perspective of Team Pohl, what we therefore have learned is the following. From their view, the pole does not fit inside. And again, that's the end of the story, according to Team Pohl. But Team Pohl also recognizes what we have now calculated, which is that the clocks in Team Barn are not in sync with one another. So according to Team Pohl, what happens is the barn folks first assess the location of this end of the pole. They say it's inside, but then they wait 24 nanoseconds before they assess the location of that side of the pole. So let me just draw that. So imagine that we now look at this situation 24 nanoseconds later. So let me draw another schematic of the barn. Now, according to Team Pohl, the barn has moved in those 24 nanoseconds, which means that even though, according to Team Pohl, this end of the pole did not fit inside the barn at the same moment as that end of the pole, they recognize that according to Team Barn, they do fit, because according to Team Barn, what happens is they wait 24 nanoseconds later. According to Team Pohl, the barn moves over. We've calculated how far that is. How far was that? That's 22 feet, so let me just record that for good measure. So if I draw a little dotted line here, a little dotted line over here, this now is 22.2 feet. So clearly, this diagram is not to scale, but the idea is correct. So according to Team Pohl, what happens is the barn moves over 22.2 feet between when Team Barn assesses this location and that location. And then, of course, according to Team Barn, the pole will fit inside. It's not measuring, according to Team Pohl, the front and the rear at the same moment. Whereas, of course, according to Team Barn, this moment and this moment are the same moment. According to Team Pohl, they are not the same moment. The relativity of simultaneity coming back with a vengeance. So that is the explanation, according to Team Pohl, of how it is that Team Barn comes to this weird conclusion that the pole fits inside, whereas they know that it doesn't fit inside. Both of these pictures are absolutely correct. They're just two different perspectives that allow us to understand how it is that not only do these two frames of reference come to a different conclusion as to whether or not the pole fits inside, but we now also understand how each team understands the other team's claim, even though they don't agree with it. Again, coming from the relativity of simultaneity. So that's the mathematics behind this way of resolving the apparent paradox of the pole in the barn. What we want to do now is to get some feeling for these ideas by working with some demonstrations, which are good to play around with these things on your own. And that's what these demonstrations are for. So let's take a look quickly at one, but you should study this in more detail. This is very similar to the demonstration that we had earlier, except now you will note that it's adorned with a little bit of extra detail. So we now have doors on the barn, one moment in time from the perspective of the barn, but not one moment in time from the perspective of the pole. And you know that because there's going to be a flash. I should have said that when it was going. Watch for the flash. And again, do this on your own. The flash is at one moment in time from the pole's perspective. The pole says, that and that. Those are same moment in time from the pole's perspective, very different moments in time from the barn's perspective. And similarly, you should work on the pole perspective too, where you'll see again the relativity of simultaneity, but now in mathematical form, fully explains this pole in the barn paradox. The twin paradox is the most famous of all paradoxes in the special theory of relativity. But before we get into it, let me just stress the most important point. There are no paradoxes, as I said earlier, in special relativity. If there were, the theory would collapse. There are, however, situations where it seems like there's a paradox. It seems like we have two perspectives that we can't somehow meld together into a coherent story. But that generally means we have to think the situation through with detail. Think it through with our understanding of the essential physics. And when we do that, all paradoxes fall to the side. The same will happen here. Okay, let's set it up. The paradox, or the seeming paradox, will involve a couple of characters. They are twins, George and Gracie. And the scenario is one that may have occurred to you in our earlier discussion of time dilation and space travel, because we are going to imagine, in this case, that Gracie goes into a spaceship. She travels out into space. We're going to have her go pretty fast. She's going to turn around and come back. Here is the issue. From George's perspective, stay at home, George, on Earth. Looking at Gracie, from his perspective, he knows how time works in special relativity. He says that her clock must be running slow, so that when she comes back, he will say that he will be older. Not as much time will have elapsed on her slow-moving clock compared to him. Gracie, however, she looks back at George, and she says to herself, look, I understand special relativity too, and it's George, from my perspective, that's moving. I'm stationary, and therefore it's his clock that's ticking off time slowly. So when I return, it should be the case that I, Gracie, am older, because less time will have elapsed on George's clock. That is the issue. Let's see that in visual form. So here is the question. There is George, first character, and let's bring in his twin. These are fraternal twins. Gracie, she gets into her spaceship, and we're going to send her off into space. So let's do that. And let's say she's going fast, so there really will be some kind of significant time dilation going on here. She goes off into space. She's going to reach some point that we will call P, the turnaround point, and she will then come back. Okay, so then the question that we are faced is, when these two guys compare the amount of time that has elapsed according to each, will it be the case that George is older than Gracie? Will his clock have ticked off more time? Will it be the case, on the other hand, that it is Gracie that is older? Will it be that more time has ticked off on her clock? Or you could even imagine a resolution that puts these two together. Maybe it's the case that each of them will have aged, each will be the same age as the other when they return? That is the question. We want to figure out which of those three scenarios is correct to resolve this seeming paradox that each says that the other's clock must be ticking slowly. Each therefore says that they should be older. Okay, so I'm going to offer you some resolution to this paradox. The deep question is, who is right? Which of these scenarios is correct? Now, you might guess that they are both right, because that has been oftentimes what we have encountered so far in special relativity. Each perspective is right, and you just have to reconcile them with your understanding of how special relativity works. So that's a natural guess, but that guess will not fly in this case. That will not work, because at the end of the journey, right, George and Gracie are together, right? So they can face one another. They can be standing right next to each other. In fact, they can even go into the same frame of reference. And there can no longer be any mismatch in their observations at that point. One cannot look at the other and say that you are older, and the other looks at the other person and says you are older. That's a contradiction. That's a paradox. That can't happen. So we cannot rely upon the kind of resolution that we have found earlier. Somebody here is right, somebody here is wrong. How do we figure out which? Well, I am going to give you the answer. It is Gracie who turns out to be younger. George turns out to be older. And I'm going to give you three explanations for that. Let me start with explanation number one, which is a simple explanation that really cuts to the heart of the matter. Where does the contradiction come from? Where does the apparent paradox come from? It comes from George saying that he can be viewed as at rest, Gracie moving, therefore her clock ticks off time slowly, and, of course, Gracie can say, I am stationary, and it's George who's moving, and therefore I can claim that it's his clock that is ticking off time more slowly. Is that valid in this situation? Well, remember, the only time that you can claim to be at rest and the rest of the world is moving by you is if you are going at constant velocity, constant speed in a fixed direction. That is manifestly not true in this case for Gracie. Gracie going out into space and then coming back. She has to turn around. And when she turns around, she has to accelerate. She slows down and then she speeds back up to get back to George on Earth. She feels that acceleration. She knows that she is moving. She is no longer moving at constant velocity. She is no longer justified in saying that she is at rest and the rest of the world is moving by her. So her perspective, her reasoning is negated by the fact that she is accelerating. She is not in an inertial frame of reference throughout the whole version of this journey, and therefore we cannot trust her conclusion. George, on the other hand, is in an inertial frame. He is at rest on Earth's surface. He does not move, subject to the issues of whether Earth's surface is an inertial frame, but those are the complexities that we are not worrying about for the discussion we are having. George's perspective, therefore, is valid. He is constant velocity throughout this entire journey. His conclusions are unassailable. They are absolutely correct, and he says that Gracie's clock is ticking off time more slowly, and therefore, when she returns, he will be older. Period. End of story. That is the resolution, or I should say a resolution of the twin paradox. We will come to other explanations as we proceed further with this deep scenario that lets us really sink our fingers into a lot of the details that we have been developing. But as a first pass to this scenario, that is the explanation. Gracie is accelerating for part of the journey. Her perspective, therefore, cannot be taken into account. She cannot say she is at rest. George is the only one who can say that, and his conclusion that he will be older is correct. Perhaps the most famous equation in all of physics is E equals mc squared. It comes right out of the ideas that we have been developing, and I'd like to first give you a sense of where it comes from, just motivating E equals mc squared. For those of you who are taking the mathematical version of this course, I will do a full derivation in short order, but let's just begin with the ideas that lead us to the possibility that energy and mass, E and m, might be deeply related. They might have some deep connection that is ultimately embodied in Einstein's famous equation, E equals mc squared. Now, to do that, I'm going to start by telling you a little story. A story that I like to call the parable of the two jousters. So it's going to be a kind of joust, but different from the one that you might have in mind. We're going to have two individuals perfectly matched. So they're going to be on identical horses, they'll have identical masses, and they're going to hold a lance, but not one that has a sharp end. We're going to imagine that there is a large metal ball at the end of the lance, and the way this joust will work, when the two combatants cross by each other, just as they are passing, each is going to lunge outward toward the other, smashing their spherical balls together, trying to knock the opponent over. So let's take a quick look at what that joust would look like. This initially was meant to be another George and Gracie animation, but I contacted Gracie. She said, talk to my agent, getting kind of diva-like. So we have a new character whose name is Evil George. So it's George versus Evil George. There they have their lances with the metallic spheres. They slam those into each other. And because they are perfectly matched, we are assured that it will be a draw, a tie. Okay, now George takes a course in special relativity, and he starts to think. He says to himself, from my perspective, I'm stationary, right? And therefore, Evil George is coming at me. And let's assume that this joust is happening at very high speeds. The horses are moving near the speed of light, let's just say, to be dramatic. And George says to himself, that means Evil George is in motion, from my view. That means Evil George's watch, his clock, is ticking off time more slowly. That means, from my perspective, Evil George, as he goes by, he may be moving quickly on his horse, but his movements will be slowed down, slow motion. So George says, this is going to be a piece of cake, because as Evil George goes by, he's going to lunge at me so slowly that I will easily be able to knock him over and win. So that is his view in his mind. So just to peer into George's perspective as he thinks about this relativistically, he says, Evil George's lance is approaching me slowly, so I should win. And yet he doesn't win. It's still a draw. So the question is, what was George leaving out? Evil George thrust the lance at him slowly. He should be able to knock him over because he is going to thrust it quickly. What has he left out? Well, if you think about it, the amount of impact that you receive from a joust of this sort depends on two things, not one. It depends on the speed of the lunge. That's absolutely the case. But it also depends on the mass of the sphere at the end. So what this tells us, because it has to be a draw again, right? Because it can't be that you change your frame of reference and you turn a draw into a win. All observers in space-time agree on the events. They may not agree on when and where they happen, but it can't be that from one perspective it's a draw, from another perspective it's a win. So we know it still has to be a draw. So how can it be that Evil George hits George with the same force even though the lance is going slowly? It must be that the mass of the sphere at the end of the lance must increase to compensate for the slow push that evil George uses. So that suggests to us that energy of motion must be able to increase the mass of an object. And in fact, we can go a little bit further. We know the degree to which evil George's lance has slowed down. It's just the time dilation factor, gamma, that we have encountered over and over again. So it must be the case that the mass at the end of evil George's lance increases by the same gamma factor to precisely compensate for the slowdown with which evil George is thrusting his lance. So that suggests to us that the mass of an object must depend upon its speed. The mass depends upon its speed, and the way it depends on the speed is the mass that it has when it's at rest multiplied by the gamma factor. Now, that is a remarkable formula, because if we look at a little demo over here, look at what this formula is telling us. As the velocity of an object gets larger and larger, this is telling us that its mass becomes bigger and bigger. So you can play with this on your own, of course, but there you see it. As the velocity of an object gets larger, its mass grows larger and larger, until as it approaches the speed of light, the mass grows without bound. Now this has a number of vital consequences. Number one, we have spoken a lot in our discussions about the speed of light, and implicitly we've always been using the fact that nothing can go faster than the speed of light. But you may have recognized I have never really established that for you. Now I have, because if you think about it, when you try to speed up an object, you've got to push on it, right? Now, if its mass gets larger because its speed increases from your initial push, to get it go faster, still you have to push it harder and harder. And in fact, as the speed of the object approaches the speed of light, its mass gets bigger and bigger and bigger, which means you need to push harder and harder and harder to get it to go faster still, until at this point you need an infinite push to get it to go beyond the speed of light. No such thing as an infinite push, and that establishes that the speed of light is a speed limit for any object that has mass. The second consequence here is that this result strongly suggests that energy and mass are interchangeable, that you can take the energy of motion, the energy of evil George's motion, it turns into, if you will, the mass of an object that he is carrying. So this interchangeability between energy and mass is itself pretty vital, but let's take it one step further still.
When an object is at rest, it still has mass, of course, m at v equal to 0, what we call the object's rest mass. So using the interchangeability of mass and energy, we're led to anticipate that the object at rest still also has energy. So let me motivate the formula for how much energy the object at rest has.
We know what the units of energy are in traditional units. You may recall it's kilograms times meters squared per second squared. If you're not familiar with that formula, don't worry about it, but this is the unit within which energy can be specified. Now, mass, of course, has units of kilograms. So for energy and mass to have the same units, we'd have to multiply mass by something with the units of meter squared per second squared. Meter squared per second squared. Well, meters per second, that's a speed. What speed would we multiply by in order to have some universal way of translating between energy and mass? Well, of course, the speed involved would be the speed of light. So this is one way of thinking about Einstein's amazing realization that energy and mass are interchangeable, sort of like dollars and euros, with the conversion factor between energy and mass being nothing but the speed of light squared. E equals mc squared. Thanks for coming along on this ride into the wondrous world of special relativity, these wild ideas that come out of Einstein's thinking about space and time, and matter and energy. Let me leave you with just one thought as you reflect back on all of the material that we've covered. All of the results that we have found, all of them fundamentally come from one idea: the constancy of the speed of light, right? That is where the relativity of simultaneity came from. Remember, forwardland and backwardland, it's the constant speed of light which makes it so that those on the train and those on the platform do not agree on what happens at the same moment. The constant speed of light is what makes clocks tick off slowly as they are moving by us, right? We use the light clock. Again, constant speed of light as it travels along the double diagonal. That is why time ticks off slow when a clock is in motion. We then parlay that into length contraction, where lengths of objects in motion appear shortened along the direction of motion. And finally, we've gone further, and we've come to this stunning realization that energy and mass are interchangeable, which is just to show that if you focus on an idea, if you focus on some new feature of the world and are really able to think it through to its logical conclusion, sometimes that results in a revolution in the way that we think about things. So go back to the rest of the course, review it, try to get a feel for these wondrous ideas, because special relativity is truly one of the crowning achievements of our species.